All right. Hello, everyone. Welcome. Thanks for coming. I'm John Howard from Solo.io, and I'm really excited to be here talking to you guys today about lessons applied building a next-generation AI proxy. Before we get into the new stuff, I think it's pretty important to look back on the kind of foundations on why we felt it was necessary to build a new thing in the first place. And I want to start way back by giving a probably very loosely accurate view of the kind of the history and evolution of proxies over time. This was all long before my time, so my understanding was back in the day, Apache HTTP server was kind of the popular thing. And as requirements on infrastructure evolved, things started to shift, right? We started to see larger scales in terms of number of requests and connections. And things like Nginx started popping up to become more dominant positions, solving things like scaling to 10,000 connections in a single proxy, for instance, a number that is now fairly small. Fast forward another 10, 12 years, we start seeing microservices rising like crazy and putting more pressure on the infrastructure again to help solve observability, connectivity, dynamic programming as pods scale up, down, left, and right. And that's where Envoy really started to take off. Envoy is the largest, most popular proxy in the CNCF, widely adopted. And now if we fast forward another 10 years or so, we're starting to see AI dominate the infrastructure space in terms of new deployments and requirements. And we started to look at what are the needs that infrastructure or that AI is bringing onto the network, right? And can we meet these with Envoy, or is this another step for an evolution? So we started looking at the problems of why you may need an AI gateway. And it's kind of a long, nuanced topic. I had a talk actually yesterday that was 30 minutes on this, but you guys get 30 seconds, so bear with me here. Some of the broad requirements may be things like deep native LLM observability. So things that are like aware of the actual prompts and responses from LLMs. So that I can understand not just that I got a 200 response from the AI model, but that I got this big body of text and that it said something like, hey, you're ugly or something mean, and we need to go audit to understand what was going on with this non-deterministic AI model, right? We may need LLM-aware rate limiting. So we're not just dealing with requests anymore, we're dealing with tokens. And I may have a single request that has 1 million tokens and costs me $5 for that one single request, right? So we don't just want to say you can send 100 requests per second. We want to say how many tokens you can use. We also may want to do failover. Again, like service failover is a common topic in a traditional API gateway, but LLM failover may look differently, right? It may be that we're sending the request to the same place, but we're just using a different model if that model has an outage or has been degraded. Or we could be failing over to a provider that uses a completely different API, like moving from OpenAI to Anthropic or something like that. To solve that type of API migration, we may also need a universal API abstraction so that as we're moving between these different providers, we're not having to change and rewrite all of our applications. And then kind of later on, we found all of these requirements, again, really applying to MCP, which is a newer protocol that I'll get into a bit more detail later. So some of these initial steps, we took these requirements and we thought, OK, these really are bringing in new requirements that we could solve with an AI native gateway. And so back about 18 months ago, which is approximately forever in the AI space, Solo.io, the company I work for, which is a company that's founded around building API gateway and service mesh solutions on top of Envoy, announced Glue AI Gateway. And how this worked was we took Envoy, and it didn't natively solve these problems, but it has a lot of extensibility points. One of these is the ability to call out to an external server, they call this the external processor, that we could basically just stream all the request headers, the request body, response body, et cetera, and modify it as much as we want. And so we took this and we integrated it with a Python sidecar that did all this AI stuff. We used Python because it was the dominant language in the AI space, and we thought we could leverage a lot of the ecosystem there to give the functionality we wanted. And so this was the initial approach we took. It worked. It was stretching the limits of Envoy to the seams. But it worked. We shipped it. It's used in production. And then along came MCP. So MCP, or Model Context Protocol, is this new-ish, again, a year ago, so new or old, depending on how you're looking at it in the AI space, protocol that aims to kind of empower LLMs with tools like accessing emails or sending a GitHub pull request or browsing the file system, so that it can't just talk to you, but it can actually interact with the world, right? So super powerful, and what's powering this whole agentic movement. So this is awesome. It's really popular, really powerful. But from a networking standpoint, we don't see this. We see this nightmare, right? If you go read the spec and you're a networking guy, you're reading it, you're like, no, no, I'm not, don't do that. Don't have state, don't make it streaming, don't do all these different things they're doing, right? But it doesn't matter because it's so popular and so successful that it has won already in this space, that it's meaning that the networking infrastructure needs to adapt to meet those needs of users, even if it may not be the easiest thing to do. So with the LLM, we were able to stretch Envoy to what we needed. But once MCP came, we said there's absolutely no way. We've already maximized what we can bend and break it to do. And that was when we decided really to start on a new proxy from the ground up that was built to solve these AI use cases, which is where Agent Gateway came. Agent Gateway really came after MCP Gateway and about 100 naming iterations in between, but we landed on Agent Gateway. And so the idea was that we would have native MCP support from the baseline. That was like the initial thing that we built the proxy around, so that it wasn't this afterthought that had to go through various extensibility layers. But we also realized that you probably don't want an MCP proxy and an LLM proxy in your standard proxy. So we added the LLM support as well, backfilled from the initial launch that we had done. Once we had done this, Google came out with an announcement, said, hey, there's this new A2A or agent-to-agent protocol. And we said, well, that's great. We have all this AI stuff here. We're going to add that as well. And so now we have all three of the kind of leading AI protocols. But we also saw that people, just because they have AI use cases, doesn't take away all the standard API gateway use cases like retries and timeouts and logging and tracing and authorization policies. So we knew we needed the full support for all of those types of standard policies in addition to the AI support. And so we also built in full support for these traditional HTTP features built on modern standards like the Kubernetes Gateway API. And while doing all this, we wanted to maintain a proxy that was fast, secure, feature-rich, and simple. And so I want to bring up kind of how we built this, building on the lessons that we've applied from years and years of using Envoy, building out things like Glue and kgateway and Istio, and how we brought those into a modern AI-native proxy. All right, so like I said, this is a new proxy we built from the ground up. We emphasized on day one for running on Kubernetes with AI-native use cases. And so like Envoy, it came out before Kubernetes, or at least basically around the same time. And so while it was very well able to be adapted into Kubernetes, it's not built for Kubernetes, right? So we decided we were going to specialize on running on Kubernetes and optimize for that use case, which is where our users are going to run this. We wrote this in Rust, which is a pragmatic choice for building a modern networking proxy in 2025. This has enabled us to leverage a really rich, extensive ecosystem of high-quality libraries that enables us to move quickly and meet the goals of our speed and security requirements. And we built this from experience with Envoy as well, but also with zTunnel from Istio. If you're not familiar, zTunnel is also a new proxy from the ground up in Rust that we built in Istio to solve a very, very specific tight use case to kind of hyper-optimize for a baseline L4 networking. But it was a kind of our first foray into departing the world of Envoy and seeing some of the benefits that we could get out of a more specialized solution. We also, though, like I said, we wanted to be full-featured, not just in the AI space, but in the general space. So while we're trying to specialize, we're also kind of broadly feature-rich. So we have all sorts of features from full gateway API conformance, HTTP rate limiting, LLM rate limiting, all sorts of authentication, authorization, rich LLM functionality like the universal API I talked about, guardrails, which is more rich authorization for LLMs, so you can check, like, does this content contain hateful or violent speech, for example? So it's more fuzzy matching. Things like MCP native authentication and authorization, support for the new Gateway API inference extension, which enables optimized load balancing when you're running your own inference workloads. So I'm not going through all these. I just want to give a glimpse that it's not a narrow LLM functionality. We have a very broad and rich set of functionality, meeting what most users are using in a gateway like Envoy today. So I want to walk through kind of the design principles that led us to being able to try and meet our fast, secure, I forget all the list, goals for the proxy. So the first one is that while we have many features, we wanted to have few building blocks to get there. And using kind of the hindsight of 10 years of building on Envoy to know what features users need and how we can build those in a manageable way without a huge bloat in complexity and requirements. So if you look at Envoy, there is a lot of features. This is just a small glimpse of the features. I felt bad putting even more words on the screen before I stopped here. So Envoy has almost every feature under the sun, but it also has a lot of extensibility points as well. So I was looking, and I came up with at least 7 extension mechanisms. I bet there's at least 10 that I missed some. Ways that you can customize and extend Envoy. There's WebAssembly, Lua, Cell, Go plugins, external processing, which is what we used in the Envoy Python thing, dynamic modules, static modules. So Envoy has grown over time as it's organically met new user requirements. And with that, it just comes more and more complexity added onto the project, right? This comes with the cost. Over the years, Envoy's performance has degraded as more and more function is added, and as the proxies become more and more abstracted to meet these different requirements. And so with Agent Gateway coming in with that experience of how users are using Envoy and other proxies, we wanted to come with a solid core that would meet the use cases, but without these over-abstract, over-complex extension points that lead to this degradation of performance. So one of the ways we did this was we standardized on Cell, Common Expression Language, which is a small expression language used in a lot of places, Envoy as well as Kubernetes and some others, as kind of one of the foundational building blocks used throughout all of our policy types. So here's an example of like access log configuration using Cell, where we have like a filter of what logs should be included, but also ability to add custom fields. Another one is like an authorization policy that again uses Cell to control what MCP tools users can access based on various attributes. So here we say that test user can only access the add tool, for example. And again, here, rate limiting. We use Cell again because Cell is used throughout the project rather than this organic fragmentation of extension mechanisms. And so here we're saying we're rate limiting based on what organization they're in and whether they are authenticated. We do recognize, though, that a lot of users have very, very bespoke extensibility requirements that can't be solved within a kind of limited environment, which is where we borrowed two of Envoy's extension mechanisms, external authorization and external processing, which allows that call out to an external module that can do basically anything you want. So with those, we felt that we could get the 99 or even 99.9% use case in terms of functionality, but with a fraction of the cost to the user. The next important thing we did was we wanted to design from the user and work backwards. One thing we've seen a lot in the Envoy space, so if you're not familiar, there's like probably 30 to 50 different networking solutions built on Envoy, and they're all adding their own APIs and abstractions on top of them under the hood using Envoy. And one of the common things you can see with these is that they very, very frequently tend to bleed Envoy-isms into their user-facing API. Right, so I'll pick on a few projects that I'm involved in so I don't feel uncomfortable picking on them. But if you look at an API like this, it's not something you would design if you went and met with users and decided, this is what you want to solve. It's really like you looked at Envoy and said, this is what Envoy can do, and I'm going to expose that to the user, right? I work on the project that has this API for 5 years. I don't know what these fields mean if you ask me. I know some of them, not all of them, right? And it's not just one example, right? This comes up again and again. And it's not just the specific namings of the field or the exact fields exposed. It's very high-level architectural decisions. Like, for example, we see users that want to do authorization rules based on the service. But Envoy makes you put that at, say, the gateway level, for example. And so there's this mismatch on how you can actually configure the thing you want to do. This happens both directly when someone comes to us and says, hey, I want this feature. And we say, well, Envoy does it this way, so we'll do it that way. But even implicitly, when I come up with a feature, because I'm so ingrained in how Envoy works, I think, well, I'll do it this way, because that's how Envoy did it, right? And subconsciously drawing us towards these Envoyisms. So we really wanted to break that and think from clean slate. What requirements does the user have? What should the API look like? And then take that and build the data plane around that. Versus what everyone else has been doing is looking at what the data plane can do and saying, how can we expose this in a nice way to the user? Which tends to not go as well. Now, tying in with this, we wanted to model the internals to meet the externals. And what I mean by that is like the user-facing APIs. And so if we look at, for example, a simple gateway API setup, if you're not familiar, I'll walk us through this. We have kind of a gateway, which defines like a single instance of the proxy and the ports we're listening on. And then we can attach a route to it that has basic routing functionality. This is basically the simplest thing you could have. It's just saying send all traffic to my echo service on port 80. In Agent Gateway, we directly map this down and use the same language and primitives in the internals of the proxy as the user-facing API. So this is what I meant by we're optimizing in native to Kubernetes. So on this right side here, I'm showing the internal representation of the configuration in Agent Gateway. I can't show a comparison to Envoy because it's like 10 megabytes and it won't fit on the screen, right? And you can see here that you can understand what this means, and there's a one-to-one mapping between every field, essentially, right? We can see I have a gateway. It's named Agent Gateway. It's the same name as the Kubernetes resource, right? I have a route. It's named Echo. It's the same name as my route resource, right? So there's this one-to-one mapping. And even the code, not just the representation of the data, but the code in the data plane follows what would logically come from the API, right? I know this sounds obvious that you would have code that says, select the listener, find the route, find the backend, send to the backend. But if you look at Envoy's internals, its model is fundamentally completely different, right? And so this makes a struggle for users to understand, debug, and build platforms on top of it. This shows up directly in user-facing things as well, like the logs. This is a short snippet of an Agent Gateway log for a request. And we can see I can see the primitives that I actually know about as a user. Like I know what a gateway and a listener and a route are because I configured that, and I can see those in the logs. Whereas in Envoy, you'll see Envoy internal details. Like here's the cluster name. Like I don't know what a cluster name is because that's an Envoy thing, not a Kubernetes thing, right? And it's not the same as a Kubernetes cluster, just to be clear. And so this is not just about the internals, but it also impacts the external user-facing things. Building on top of this some more, we want to optimize based on the real patterns we see with users, right? Like there's a common trends in how many gateways and routes and services and pods a user is typically going to have and how often they're going to change, right? A pod, you probably have many pods more than you have gateways, right? And those pods are probably constantly changing because you have autoscalers, you're having nodes going up and down, right? So we specifically recognize those patterns and optimize for them. So if we look at Envoy internal representation, for example, this is super loosely oversimplified, but it's just to get the point across. You'll see a lot of lists of resources. Like we have a list of domains, and under that, a list of routes within each domain. And so if I wanted to change one route, I need to go push this entire updated set of objects down to Envoy, which is very computationally expensive for the control plane and for the data plane itself. There are some areas where Envoy is able to kind of split these up into smaller and smaller chunks, but there's only so small it can get chunked, and the overhead of each chunk ends up actually being quite large as it gets down into smaller scale. So in Agent Gateway, we took a different approach and said instead of having these big lists, we're going to have kind of the bottom level resources point up to the resources that they're a part of. And so a route is going to be a standalone thing that can be independently updated, and it just has a single pointer to the listener it's a part of. And the listeners, again, are independent and just point it to the gateways. And it's the same thing for the pod to service relationship. And so, for example, like pods I mentioned, we're constantly turning pods up and down, right? In Agent Gateway, that just results in like a 100-byte update down to the data plane to update that. Whereas in Envoy and most solutions, you'll end up pushing maybe multiple kilobytes or even megabytes of data to recompute this big block of data. This has very, very real-world implications, right? This is a graph of the control plane of Agent Gateway versus Envoy Gateway for a test that's scaling a bunch of pods up and down. If we zoom out a bit, I didn't want to overload you at once, but this is the same charts, but just showing the memory and CPU of the data plane and control plane. And you can see there's about a 25 to 50x reduction across all metrics, and that's directly tied to these design principles that enabled this. Lastly, we wanted to make sure we build natively. So we had kind of talked a bit about the Python external callout previously. we saw a lot of issues with that, both from a complexity, reliability, and scale performance standpoint. The more you have to hop back and forth between two processes, obviously each hop has a cost, but it's also very hard to pass the context you need between them, right? And so we were constantly trying to get information from one process back into the other in the time we needed it to get there, right? And so we felt that building everything natively in one proxy would solve this a lot. And I want to go a bit more deep dive into how this is looking in some other projects as well. And I just want to clarify, I meant to say this earlier, but the company I work for is entirely built on Envoy solutions. So nothing I'm saying here is meant to hate on Envoy. This is more there's a lot of great things that Envoy is doing. This is more about talking about how we're optimizing from the hindsight that we've learned in Envoy for building some more purpose-built solutions. So if there's a project that extends Envoy called the Envoy AI Gateway project that has added MCP support recently. And the architecture for how they do that is somewhat similar to what I talked about previously, where they have Envoy, but they have an external processor sidecar to help them. This happens to be written in Go, but it's not so much different than what we had initially. But like us, they found that even with this external callout, the MCP protocol was too complicated to manage within Envoy directly. And so they added a second sidecar that was not using an external processing, but would actually forward the entire request through the MCP sidecar and do whatever they do in their MCP Golang code, forward it back to Envoy to finally go to the destination. And so each request is going and bouncing around between these different processes. And so of course they have a control plane to manage Envoy, like most people do. But this control plane doesn't natively support this AI functionality. So they have a control plane extension, almost like an external processor, but for the control plane. And because now they have these three different components that all need to be dynamically updated, they also have that control plane configure all three of these. And so what we end up with is this very complex maze of where is my data going? What is actually happening? And when you try to debug the system, it's incredibly complicated, right? It's very hard to see what's going wrong, what's actually happening, where the data is flowing, et cetera. So when we're talking about building natively, we see this drastically simplified, where we just have a data plane that does all the processing we need and a control plane that configures it, right? And we saw tremendous benefits from this. So we did some performance analysis of MCP traffic, comparing the agent gateway approach versus the Envoy AI gateway approach. And we saw almost 100x improvement in throughput of traffic for MCP. This is directly related to this need to go bouncing back and forth between all these processes rather than doing it natively in the proxy. For LLM throughput, so this is like calling OpenAI or Anthropic, we saw pretty similar, not quite as extreme as the 100x because they're only using the external processing, not with the additional hop. We saw about a 10x improvement with Agent Gateway natively. And so the last thing, design principle, was to keep it open. And by that, I mean open source, open governance. Everything I've talked about today, except for the very first slide where I talked about our initial gateway, is open source. It's donated to the Linux Foundation. That's why I'm able to talk about it here today. And so obviously, I don't think anyone's really interested in a closed source data plane these days. So it was kind of an obvious choice for us. So with that, I think that's it. And I thank you all for coming. I've got a few resources here. I honestly don't remember what the QR code goes to, so hopefully it's something interesting. But we've got the Agent Gateway website. If you'd like to check it out, drop us a star. We also have a lot of the performance numbers I showed are from this Gateway API benchmark. That's kind of an open, reproducible benchmark that I just showed a snippet of it, but we test all sorts of different gateways. This was started before Agent Gateway as well, so it has a lot of information on just general gateway API comparisons at different types of tests like route scale, throughput, things like that. And then if you like this talk, I blog about all this type of stuff as well on my blog sometimes. So if you want to read up more, feel free to check it out. That's all. Thank you, guys.